Alright, this is section 12.4, testing the significance of a correlation coefficient. So this is the first problem, problem number 1, dealing with giant sequoia trees. It says giant sequoia trees, Sequoia giganteum, are the world's largest trees by volume. The natural distribution of giant sequoia trees is restricted to the limited area of the western Sierra Nevada, California. Is there a positive correlation between the height of a tree and its circumference? Here are the heights and circumferences, both in feet, of 12 giant sequoia trees. At a level of significance, tests the claim that there is a positive correlation between the height or circumference of giant sequoia trees. Use alpha is equal to 10%. Assume that the heights and circumferences of the sequoia dendron trees is a bivariate normal distribution. Alright, so here, listed here, trees 10 through 12 from our local giant sequoia tree national forest. You have trees 1 through 12 there, and I think they all have each one of them unique names. So there are listed their height and circumference. Of course, that is, I think this is recorded data here from 2012, and so certainly these heights and circumferences are welcome to change over time. So what we're trying to do is prove that there's some sort of correlation, and a little preliminary stuff I need to talk about is also this concept of rho. And so even in what we naturally want to do here is see there's some sort of pattern, and so since that we have each one of these trees, what we can do is turn each one of these order pairs into an XY order pair, I guess, in that way, looking at that in R2, in a coordinate system, so that you have an x-axis and y-axis, and it really doesn't matter in a case like, one affects the other, but what does matter is a couple of things here, and along with the idea that I'm going to outline in just a second, that this bivariate normal distribution, that needs to be true about each one of those. So in other words, that x and y are normally distributed, but more particularly that for every, let me point out here, for every isolated x value, therefore the whole distribution of, as I single this out, therefore this whole distribution of y is normally distributed. As I kind of move and progressively go through here, if I change that to another x value, then the y is still going to be normally distributed, and vice versa. So that works that way for x, and then vice versa for y as well. So for every singly isolated value in the Ranger domain, then the other element is also normally distributed. So that's what they mean by the bivariate normal distribution. But also needs to be true as well, and we won't get into too much detail. This is that you have to have ordinal data. And the safest way to do that is by, just kind of ignoring that idea, like even or ordinal, just say, just go with a numerical. So if it's number, obviously we don't have to worry about it. It is a order set. So in other words, if we had gender, males versus females, we can't order that. You couldn't consider that to do anything with a correlation. So it has to be numerical in that nature, some sort of rating system or something like that. In this case, we're dealing in feet, so it's perfect. So we certainly have to be careful before we just do any sort of correlation. But in the moment of this, by looking at the x and y order pairs, we can plot them and see if there's some sort of pattern. So coming here right next door, if we look at an x and y axis, y-axis, x-axis, suppose that the order pairs do something like this. Well, this is obviously these are very rare in this nature, but if you had something, then maybe I could say that there's some sort of linear trend here, which we call linear correlation. We could have a downward trend, meaning that it starts up high and then goes down, so maybe it looks something like this. And again, in this way, this is very rare for this to even happen, but you could have some sort of linear trend. And then the other aspect of that, and these are why these are called scatter plots, is that you could have a bunch of dots, like looking into the stars at night. They kind of look like this, and so perhaps in that respect that there is no trend at all, and we'd have to be able to prove that. And so the best way to prove that, of course, with linear regression is using a number, and then we're going to end up sampling that between -1 and +1, and then we have 0 in the middle. So in order to set this up, we'll talk about this later, that in this realm here we have what lives R. or it could be, or rho. So R is, actually I'm going to start with rho. Rho is a population correlation coefficient. And then R is the sample correlation coefficient. And the idea is that they all live in this realm here between -1 and +1. So starting off with -1, -1 means a strong negative correlation. +1 means a strong positive correlation. So if you want to prove that you have some sort of correlation, you have to say either it's a negative or positive. Now, however, in the middle, 0 means no correlation. So in terms of rho and R, suppose that I had, some sort of dividing point here. How close to +1 do you need to be in order to say that you have a positive correlation, or close to -1 that you have a negative correlation? But in fact, if you're at 0, then you have no correlation at all. So R and rho give us the idea, or this aspect of being able to tell if we have a correlation without specifically just looking at the graph. Because certainly in some ways here, if you're looking at a scatter plot that looks like this, you may want to say that you probably don't have any type of correlation. But suppose another way here, then we're talking about nonlinear, that you could have something that has some sort of pattern. It's just not linear. So suppose it just kind of goes up, kind of like a parabola, a downward shaped parabola. So we would say that that has some sort of trend. It's just not linear. And this would not be the test to do to establish a trend that was nonlinear, but it could arise with some of those questions. So this is strictly just for testing a linear correlation, in this case more specifically a +1. So jumping back down to here just for a second before we go to our populations, we're going to assume that from the very beginning that rho is equal to 0. And we'll do that all the time, no matter what, if this is trying to prove a positive or negative correlation. So here from the very beginning, so we want to assume no correlation. You always want to do that. But of course, beyond the benefit of the doubt, if you can prove that, in this case here, they want to prove that it's positive, that means that rho, we want to try to prove that rho, the population correlation coefficient, again, that number between -1 and +1 is close. In this case, we want it close to +1 as much as possible, or in this case, far away from 0. So we'll just do this. We're going to try to prove a positive correlation. Okay, we'll do the best I can. We do that within that certain realm of degrees of freedom. So again, going back over this, we have order pairs here that we could plot in an XY plane. However, looks can be deceiving. Looks can be deceiving. Therefore, we use the scale between -1 and +1 to better offset and have a better judgment rather than just looking at a graph. So many times the graphs are deceiving. You can't make critical judgments based upon the look of a graph, even though all administrators that I work with at work, they make that same mistake all the time, and it's really frustrating that they make that kind of mistake. So you have to be able to prove your claims here, and this is certainly this test that we're going to do in order to prove your claims, rather just basing all of your information by looking at a graph. Never do that. Never make any conclusions solely upon a graph. So I want to move this up to the top here, and again emphasize in on rho is the parameter and R is the statistic. So here's new parameter, new statistic for the section for 12.4, dealing with this multivariate case here. Well, now that we have that talked about rho here, let's go talk about our populations. And in this way here, populations are going to be based upon what we're collecting. In this case, we're collecting giant sequoia trees of that sort of nature. So for both of these, we're going to have the set of all. So with a special condition though, so the set of all giant sequoia trees I'll do that for both again here. So the set of all giant sequoia trees okay, so for the first population there, the experiment group, you're going to say in which there is a correlation, in which there is a correlation between, you only want to fit that in there, between height and circumference, between its height and circumference. However, for the population number 2, the control group, we want to just assume that there is no correlation. So it really is black and white in that way, because we're dealing with a multivariate case here. We're putting two ideas into one and simply making it easier here that there is versus there is not. Again here, I'm just going to put in the word no. There is no correlation. And that's how all those are going to go with in the case for population 1 and 2. So population 1 is, population 2 is not. Despite the fact, even coming up here at the top, despite the fact that we want to prove a positive correlation, we just want to simply say that there is and there isn't to start off with, but obviously from a researcher's point of view here, we want to try to prove that there is a positive correlation. So let's go ahead and start that off here, starting off with verifying the requirements. There's a multiple number of requirements, of course, but we're going to try to keep it simple here. But the main fact that both X and Y are bivariate normal. And if we can get that result, then that would imply to use the t-distribution. So a lot of these concepts are locked in place. That bivariate implies t here. We have to know it's bivariately normal. It is difficult to prove that there is a bivariate normal distribution. So simply, we'll take for the fact that it is proven to be bivariate normal without having to go through all that headache. Not that it necessarily is, but certainly a lot more time consuming than that it's worth. So make sure that anytime you're doing a correlation, you just don't run and do a correlation. We have to have the requirements met before we move forward. So let's go along with that with part 3 here, and knowing that it was bivariately normal. So here we're dealing with a t-distribution. Let's go on and figure out what the cutoff score is for significance here. Here for this problem, we know that alpha is equal to 10%. That is 0.10. You can see it there at the top that is that number. Again, that's equal to 10%. Because we're not doing a two-tailed test here, we're going to keep it as, we're going to be on the right side. But here, degrees of freedom is just slightly changed. Rather than it being, like for goodness of fit, like k minus 1, here this is n minus 2. So again, if we're dealing with two groups and we're trying to bring into one, this is where we want to change that in that case here. It gets a little more complicated with it. In this case with the correlation, but it's the degrees of freedom is sample size minus 2. And being more specific here, since we're dealing with the 12 giant sequoia trees, then our output is going to be equal to 10. And also to add to that, because we want to try to prove it's a positive correlation, this is going to be, again, a right tail. So very similar to 9.4 on dependent. So right tail test. Okay, so for positive right tail, and we're good to go there. So let's go back and here and jump over to GeoGebra and find out that value for the cutoff point for significance. But there's a lot of required definitions here that degrees of freedom is n minus 2. We want to try to prove it's a student t distribution. So that always goes with correlation. All right, so go back over here to t distribution, and then degrees of freedom. Okay, perfect there, it's at 10. Now what we're going to do is go to choose the right and put in that level of significance at 10%, 0.10. All right, there's our first cutoff point there. Rounding the four places there, 1.3722, 1.3722. Let's just jump back over here. 1.3722. All right, there's our cutoff point there for significance. And that's equal to T naught. That's our cutoff point. That is our solution for part 3. I'll shade 10% on that side. And kin here from 0 in this case implies that we have no correlation. So what I'm trying to do is be as far away from the center as possible. If I can prove I'm past the cutoff point, then I can prove I have a significant positive correlation. So let's go ahead and try to do that. Let's go ahead and collect our sample and see what happens here for step 4. Write down all the necessary stats. So for correlation, what you're going to do is you need two things. You need the sample size. In this case, we have the 12 trees. Giant sequoia trees, I'll just put here 12 trees. And then, so that's for N. And then the next one we want is that sample correlation coefficient. Here, I'm just going to go and write down the number, but I want to show you where to find this. So the answers for the sample correlation coefficient is 0.3895. And again, that number only applies to between -1 and +1. I had a professor at Fresno State talked about how difficult this proof was, that you didn't really want to try to attempt it. So we'll just take, I'm not saying that we can't, prove that. It certainly needs at least a graduate level of mathematics to be able to look at some sort of proof in that way. But we're a little bit more than third. We're somewhere between there, like that third halfway point there. So it doesn't look good. I mean, on the scale, it doesn't look like I'm close enough to +1 to try to prove that I have a positive correlation here. And you certainly want to do that. So again here, the closer you are to +1, the more you met that goal to prove that there's a positive correlation. I'm not quite convinced, but it just really depends upon the level of significance. So let's go ahead and slide here right next door. Oh wait, before we do that, let me show you where the 0.3895 comes from. So on the list on modules, I have the list of calculators there, and instead of the other one that we use from calculator.net, use this one from statistics.com, and I have the link on there for the correlation. So what I want to end up doing is I put in those numbers in here for the 12 giant sequoia trees. I entered in the heights, entered in their circumferences in terms of their feet, went and clicked on the submit button, and I got the report there for all the different values. I think they just do a brief, let me see here, a real brief summary. Here it is here. All you really need is like kind of from this first part up here at the top, like sentence number 2, it says the value of R is 0.3895. Done. That's all we need. Grab that number, you're good to go there. There's other aspects of that too, as far as the sample correlation coefficient goes. Like I'm certainly here down the bottom, it shows you for each component there how to do that stuff by hand, like the sum of the squares and the sum of the values to raise the second power. And I'm pretty sure they report what R squared is, the coefficient of determination as well. We certainly don't need that. So just look, don't worry about R squared. You just need R, the 3895. When we start talking about, here it is here, the coefficient of determination, that'll come later. And think about R squared. Okay, I don't want to get on the tangent, but the only thing we need here is the value R, the 3895. So that will come into play here, and the reason why the second power is that we're going to fold that over the -1 to +1. I can't really illustrate here because you can't see my hands moving, but just rest assured that R squared has to deal with another class that you may have to take with statistics later. So let's go ahead and standardize the R value and figure out where we're at there on that scale between -3 and +3. So here's the formula for that. So T is equal to, this one's a little complicated one, so let me just kind of slowly write this out here. R minus 0 divided by a large square root here, and inside that square root we have a fraction, and in the numerator of that fraction is 1 minus R squared. close parentheses, divided by n minus 2, that degrees of freedom. Okay, so one of the things to point out here, just like it was with the dependent means, that this will always be 0. And again, that's because we're assuming that rho is equal to 0. That's kind of that claim, and we've done that before, like in chapter 9, where you take the sample, the statistic, and minus the claim. Since our claim is 0, that's always going to be 0. Filling in for the r value, let's kind of slide in next door. That's at 3895. That's going to go right here, but also that's going to go inside the square root here at r squared. You certainly have to be careful about raising that second power, because order of operations, let me write this a little bit smaller here. Order of operations is going to say that I want you to square first before subtracting from 1. So then certainly go through parentheses, exponents, multiplication to division, left to right, addition and subtraction from left to right. So we want to square the r value before you subtract it from 1. This doesn't say, let me kind of like outline this. This here, this 1 minus r squared doesn't say, 1 minus r then to the second power. It doesn't say that. You want to square, raise r to the second power, then minus from 1 is how that procedure is done. Certainly you want to do that first before you divide by the degrees of freedom, then square root, and then divide into that number up there. But if you have a graphing calculator, or you're using some sort of web-based calculator, there's a lot better, easier on you to use, and it's a good way to double check yourself. So certainly if I go ahead and slide out my calculator, move this up here, there's just no way I can make an attempt out of it. I really don't think that there's any way I can get this thing to calculate that t-value. I'm certainly going to try. Maybe have to switch over to scientific mode and see if I can use that instead. But the answer that we're looking for here is 1.3373. So let me write that down. Before we get started here, I've already calculated this stuff out ahead of time, but we're looking for, if you do this correctly, 1.3722. No, I'm sorry, that was the last answer. 1.3373. That's where we're looking for the standardized score, given those statistics. So let's go ahead and let me just give it a try here with the calculator and see how this goes in scientific mode. So my attempt to do that is, let me do this parentheses thing first. Oh, how am I going to do this? Double checking on, I think we're going to do the square root first, and then, this may not be possible on this. Certainly you want to upgrade to a better calculator. I'm going to give it a try. All right. Enough of this. Okay, so 1 minus, we want to take that r value, 0.38, I may fail on this, but I'm going to give it a go anyway, 95. I want to square that number, then subtract from 1. Now what I'm going to do is divide that by 10, the degrees of freedom, and now square root that. So that's my denominator, but what I want to do is make it a denominator by pushing the reciprocal button there at the top, the 1 over x value. That throws that in the denominator, and then multiply that times the numerator, which is r minus 0. Or in other words, anything minus 0 is the number itself, or times where's the r value? 0.3895. Oh, there it is. I got it. Not easy to do if you have a small little scientific calculator. You may want to have something with a bigger screen. Mathway is great. And I know I have Mathway on here, so let me go and grab that in my list of calculators. Let's jump over here to, where's Mathway? Yeah, here it is, here, Mathway. And I mean, you can pay for upgraded versions for this stuff, or for a subscription. And probably won't load, it may need an update. Okay, let's see if this will change. I don't think I have this locked. Maybe this is only for iPhone. No, I don't have my screen locked. Looks like it's only for the iPhone screen, not the iPad. But that's okay. So with this, you can just go from here, use your parentheses, type in the R value, 0.3895 minus 0, close parentheses, then divide by, where's my little division? There's the division there. Square root that, and then in parentheses, you're going to have to double up on that, but you've got inside the parentheses 1 minus, start type here, 1 minus 0.3895 squared. I'm going to raise that to the second power. So where's my caret symbol? Okay, so right here I have that. Maybe I would click that first and put in the second power there. Okay, great. Now I want to arrow over. So let me arrow over to the right and then close parenthesis. Then divide that by, and it should still be in the square root there. Yeah, divide by 10. And then we go ahead and enter. It'll naturally just follow through the order of operations, and there you go. So there's the answer, 1.3373. Same answer that I got. So I think some of these web-based versions, make it a little easier to do than what I did on my little inexpensive scientific calculator. So in some ways you may need to upgrade to get, just like that. Here we go. To get that to work out better for this stuff. Coming down here for the p-value, we can see here that we want to do another right tail so that t is greater than, pointing to the right of that answer that we just got, 1.3772. 773, to find the p-value. So I'm going to have to jump back over to GeoGebra to do that. But just to point out here that since the cutoff point was 1.3772, that this failed. This is just slightly short of that cutoff point there, and was enough to show significance. So, therefore, this is going to be a little more than 10% when we go ahead and find the p-value. So let's jump back over and calculate that. We're here back to GeoGebra. Again, grab that student t. Almost wrapping up this problem here. Okay, student t distribution. We don't have to change the degrees of freedom. Again, have that bracket open to the right, but then this middle box down here. So again, go with that 1.3373 and click back there to the right. There you can see it's a little, slightly more than 10%, 1054. So therefore, this is more than the level of significance, again at 10.54%. So it's greater than alpha. That again shows proof that this does fail. We failed to reject the null hypothesis. That's too bad, but from the assumption there from the very beginning, we assumed that there was no correlation. We just didn't have enough evidence to prove otherwise. So that'll do it here. And in a lot of cases that you may think, like, yeah, there's probably is, and I would think myself that there probably is a correlation between the height and circumference. It makes total sense to do that. We just didn't have, probably in this case, we came pretty close to that. We may have not had enough trees to try to prove that otherwise, but that'll do it there. So this problem is for 12.4. For section 12.4, testing the significance of a correlation coefficient.